Okay, for this section, we're going to talk about functions of several variables. So we're used to looking at functions that just have one variable. We're usually looking at like y equals f of x or y equals f of t. Here, x is our independent variable because it can take in any value we want, but then y is determined by some function. So y is a dependent variable, depends upon what x is. But first of all, we say that this function inputs a real number and outputs a real number. So this boldface r here is the real numbers. So we say that it's a function that goes from r to r because it inputs a real number and outputs a real number. But there's really no reason that we couldn't have multiple independent variables, so multiple things that we plug into a function and output. So we're going to see some examples of this. So let's let S be the score, your score in this class. So we know that's a function of four different things. It's a function of your homework score, which we'll denote as x1, your midterm 1 score, which we'll denote as x2, and your midterm 2 score denoted x3, and then your final exam score, which we'll denote as x4. So your final score in the class depends upon all of these different variables, and these are all independent variables. So in terms of the function that we're given for this class, is your final score is this function f of x1, x2, and x3, and x4, and it's given by 0.3 times x1 plus 0.15 times x2 plus 0.15 times x3 plus 0.4 times x4. So for example, if we want to evaluate this, suppose you scored a 95 on your homework, 75 on midterm 1, 80 on midterm 2, and 83 on the final exam. Then we'd plug those values into f for x1, x2, x3, and x4 and evaluate our formula on that. And you see if you do that out, you get 84.995. So that's how you'd evaluate a function that has multiple variables. And in this case, notice we have four independent variables. We have four input variables and one output variable. So this is a function that goes from R4, because we have four different real numbers inputting, and goes to R1 because we have one output variable. So here's another example. This one just has two variables, which is going to be the type we're going to encounter most in this section. So we let f of xy be x squared times cosine of y plus sine of y. So let's just view how we would evaluate this at a particular point. So if I take x to be equal to 2 and y to be equal to pi over 3, just everywhere where there's an x, we replace it with a 2, and everywhere where there's a y, we replace it with pi over 3. So we see f of 2 comma pi over 3 is 2 squared times cosine of pi over 3 plus sine of pi over 3. And so this is 4 times 1/2 plus square root of 3 over 2, which is just 2 plus square root of 3 over 2. So we evaluate these functions just like you evaluate a function of one variable. We just have more inputs that go in and more places we have to replace the variables. Okay, and notice again we have two input variables and one output variable. So this is a function that we would view as going from R2 into R. Okay, since we've had so far just multiple variables inputting and only one output, we'll switch that now. So we'll input a variable t and output that to two things. So we get a cosine of t and a sine t. So we input 1, output 2. And so this is a function that goes from R to R2. And notice this is just the familiar circle of radius 1 centered at the origin. For this section, though, we're going to focus on functions that input more than one variable and output one variable. Okay, so if we have a function of two variables, we can graph this function in 3 space. So if you think of, you always go up one dimension here. So if we have input one variable and output another variable, when we graph those functions, you had an x-axis for your input variable and a y-axis for your output variable. Now we have the xy plane for our input x and y, and then we're going to have a z-axis for our output variable. So let's introduce what 3 space actually looks like. So here we have, you can see the xy plane here. So this is our x-axis with x in the positive direction, and this is our y-axis with y going in the positive direction here. And then we introduce a new axis that goes in 3 dimensions. So this is the z-axis. So now we have 3 axes here, and this is a 3-dimensional space. There is an important thing here to have the correct orientation so that we know that this direction is Z and not the downward direction. So if you were to lay your right hand along the x-axis, so your fingers are pointing in the positive direction, so your fingers will be pointing toward x, and you curl your fingers towards the y-axis, that'll make your thumb point in the direction, and that direction that your thumb point should be in the Z direction. So you can go ahead and try that, where hold your hands that's pointing the same direction as X, curl your fingers towards Y, and you'll see that your thumb points in the Z direction. You have to use your right hand for this for it to work out properly. If you do this the other way, with your left hand, say, everything would just come out with negative signs. So you'd have a different axis than everyone else would be using. Okay, and so here we're going to go ahead and put a point onto the graph so you can kind of see how we graph things. So this is the point 1, 2, 3. So we would go 1 in the x direction, and then we go 2 in the y direction, and then we go up 3 to get to here. So 1, and then 2, and then up 3. And that's how we get to that point 1, 2, 3. Okay, so the first coordinate is x, second coordinate is y, third coordinate is z. Okay, so now let's see some graphs and how this works. So we know in 2 space, so what we've been using in Calc 1 and in college algebra, say, we have a line is given by y equals mx plus b. In this case, in 3 dimensions, a plane, the similar equation gives a plane. So if I take z is equal to z0 plus a times x minus x0 plus b times y minus y0, where z0, a, b, x0, and y0 are all constants, then this gives a plane. Planes are going to be very important, so we want to remember that this is what planes look like. So if I take a particular example here, so here z0 is equal to 2, a is equal to 3, x0 is 2, b is 5, and y0 is negative 1, we get a plane that looks like this. Okay, so just a flat plane. Another function that that encounters often, and I like to use as kind of my default graph when I'm trying to demonstrate something, is called a paraboloid. So you can think of this as like a parabola. It's just generalized to one more dimension. So it looks like z is equal to a plus b times x squared plus c times y squared. So here's an example of one. Z is equal to 10 minus x squared minus 2y squared. So here a is equal to 10, b is negative 1, and c is negative 2. Okay, and so you can just see here, it looks kind of like a bowl upside down in this case. We can look at other functions as well. So in this case, let's look at z is equal to sine of x. So notice there's no y variable here. So really all the action is happening in the xz plane. So we can graph z is equal to sine of x in the xz plane. It's going to look just like your normal sine curve. And then you just extend it in 3 space because the y variable doesn't come into play. So you can see as you go along here, this is just z is equal to sine of x. It's just a normal sine curve. And then any value of y will work with it because there's no y in the equation. So it kind of just extends out as a wave. And it's not always easy to graph functions. Just like if I gave you a random function in one variable, a lot of times you have to use a calculator or a computer to graph that. Same thing here. It's not easy to just graph a random function that you're given, but computers are very good at this. So for example, if we look at a function z is equal to sine x plus cosine y, it doesn't look like a particularly complicated function, but this is what the graph of that looks like. So you can see it's kind of waves in each direction, but it does look like kind of a mess as well. It wouldn't necessarily be super easy to graph by hand. So in addition to graphing using the computer, there's another thing we can use to help us visualize 3 space. So for instance, most of you have seen topographic maps before if you've considered hiking, or you've seen like weather maps where they show you like the temperatures at various spaces and things like this. So if we look at this topographic map of Yosemite National Park, you can see as you go along these curves, it's a little hard to see, but they have numbers along these, and these are telling you the height. So as you walk along this curve here, you'd be staying the same height. And different curves have different heights on them. And so we can generalize this. So basically this is a way that we're able to take the different elevations in Yosemite Park and illustrate those on a 2-dimensional picture here. So we want to do the same thing with our graphs in 3-space. So we refer to these rather than as topographic maps as contour plots. So let's look back at the function we had before, the paraboloid of z is equal to 10 minus x squared minus 2y squared. So this is our graph to refresh our memory on that. And so what we do is we just draw for each value of z, we see what does that curve look like. So if I fix a value of z, so for instance, if I took z is equal to 0, I would have the equation 10 is equal to x squared plus 2y squared. So that would be an ellipse. And we can do that for various values of z and see we graph them on here. So we have these different ellipses. And now rather than having a three-dimensional graph, we see, okay, well, if I fix a value of z, say z is equal to negative 50, then that's going to give me this curve here. So as I walk along this curve, I would be going at the same height around. So think if I fix a height z and I walk around, and I'm staying at that same height, that's giving me an ellipse. So that's what this contour plot's doing. So that if you were drawing one by hand, this is how you would draw it. You'd fix some values of z, and you'd see what those curves would give you. So for instance, z is equal to negative 50. If I bring that to the other side and have a 60, so 60 would be equal to x squared plus 2y squared. So that would give us a parabola or an ellipse again. And if you use a computer, you can also include colors on this that kind of tell you, like, these ones in between here are between minus 50 and minus 100 and so on. So it's a little bit nicer of a picture, but the picture with just black and white is enough to illustrate what's going on as well. So if we looked at the z is equal to, back to the more complicated function of z is equal to sine x plus cosine y, remember this is our graph here, a bunch of bumps. So in this case, our contour plot would look like this. So you can see you're getting kind of lines here where the value is set, and then you get these different plots. And notice, so these ones are negative, so these would be going down, and these values are positive, so these are the bumps that are going up. So the ones down here would be, see these ones down here, these would be the negative ones, and these ones would be the positive ones. And again, we can color this in as well, and this makes it a little bit more obvious that these bumps are different, because even if you couldn't read the numbers, you can see, well, these are different colors, so they're not going to be the same contour. And then let's consider one more function. So if we look at the function z is equal to square root of x squared plus y squared, this gives us a cone. And so if we do contour plots of this, if I pick a particular value of z here, obviously they all need to be bigger than or equal to 0, or they can't be equal to a square root. But suppose I pick like z is equal to 2, I would have 2 is equal to square root of x squared plus y squared. So if I square both sides, I get x squared plus y squared is equal to 4. So the contours of this are going to be just circles. So what we see here, there's just a bunch of circles. And generally, the idea is the closer together the contours are, the steeper it is, assuming that they're the same distance apart each time. So here's with color included. Okay, so that gives you an idea of functions of more than one variable, kind of how to work with them in terms of just inputting things, and then how to graph them. And then these contour plots help you to be able to figure out, well, how do I visualize a graph in 3D if I don't necessarily have a computer to work with?